Hello, dear students. Good afternoon. Good afternoon to one and all. Good afternoon, Harish. Good afternoon, Valenki. Good afternoon. Very good afternoon to all of you. Am I audible? Am I audible and visible to all of you? Yes. Good afternoon, Rohit. So I'm audible, right? All of you can able to hear my voice, right? Okay. So without wasting the time, so let's continue with the today's session. So before continuing with the solutions new topic, so now I would like to give you a recall test from the topic which we have discussed in the previous class. Okay, because our previous class was on last Tuesday, right? So it's been 1 week gap. So let us recall the previous class topics with some questions. Then we will move on to the new topics today. Okay. So here I have taken two questions for you. So in the last class, majorly we have discussed about the concentration terms, right? So there were 7 concentration terms we have discussed, and out of those 7, I have taken 2 terms for you, and you have to give me the answer for these 2 questions. Okay. So what is molarity and what is mole fraction? So first of all, give me the answer for molarity. What is molarity? So without seeing your notebook and book, you have to give me the answer for this. You can put it in the chat box also. What is molarity? I want all of you to try the answer for this 2 questions. You can put the definition also, or you can give me the answer in terms of formula. Molarity is equal to moles by mass. Sure? Harish, are you sure? Rohit is saying it is moles by volume. Okay. Rohit's answer is partially correct, but moles of what? Is it moles of solvent or moles of solute? And also about volume, is it for solvent or is it for solute or is it for solution? So that you have to mention, right? Yeah, very good. So molarity is the number of moles of solute. Very good, Pushpa. Present in 1 liter of the solution. Yeah, good. Good, Rohit. So it is the number of molarity is equal to number of moles of solute divided by volume of solution. Volume of solution in liter, right? So this is the formula. Very good. What about for mole fraction? What is the formula for mole fraction? Suppose if I have 2 components, component 1 and component 2 here. Now I want to find out, or let me take this as A and B, okay? Component A and component B. So now if I want to find out the number of moles of A, I mean the mole fraction of A, what I have to do, which formula I have to use? Mole fraction is denoted by the letter X, right? So what is the formula to find out the mole fraction of component A in the solution? Moles of moles of the solution. Is it so? Moles of A by moles of the solution. Na by, very good, Rukmini. Great. Great, great. Very good, very good. So many of you are giving me the correct answer. So mole fraction is nothing but number of moles of that particular component divided by total number of moles, right? So here I have only 2 components. So the total number of moles will be Na plus Nb. This is the formula to find out the mole fraction of A. Very good. So like this, we have studied molality, mass percentage, volume percentage, and many concentration terms. So now in today's session, we are going to learn about the solid and liquid solution and gas in liquid solution and Henry's law. And thirdly, if time permits, we will discuss the Raoult's law also. Okay. So now let's start with the solid and liquid solution. Solid and liquid solution means the solubility. The solubility of solids in liquids. Okay, so let's start. What is meant by solubility? So what do you understand from the term solubility? Can you guys try the answer for this? What is solubility? Give the definition for it. Can anyone give me the definition for solubility? Very easy, no? What do you understand from the term solubility, students? Maximum amount of solute dissolved in a solvent. So Harish is saying, giving this definition. Very good, Harish. You are exactly correct. So the maximum amount of the substance that can be dissolved in a specified amount of solvent. Okay, so we should have a specified amount of solvent at a specified temperature. So that is called as solubility. Okay, suppose I may have some 100 ml of water here. I may have some 100 ml of water. Okay, and this is the solvent. 100 ml of water is the solvent here. This is the specified amount. 100 is the specified amount of solvent. And to this, I may add some 20 grams of sugar. Okay. And here sugar is the solute. Okay. So maximum I can add only 20 gram. Maximum I can add only 20 grams. So that is the maximum amount of the substance that can be dissolved in a 100 ml of water. Okay. If I add 25 gram or if I add 30 gram or 50 gram, so this 100 ml water cannot dissolve that 50 gram of sugar. Okay. Means only 20 gram can be dissolved in this 100 ml of water. That is the maximum amount of solute or the substance that can be dissolved in a specified amount of solvent at a specified temperature. Okay, so temperature may be, what to say, at the room temperature itself, the sugar molecules, the sugar particles will get dissolved in water molecule, and also you can heat it. Even if you heat it, the solute particles may get dissolved in the water. Okay, so temperature should be very specific and the solvent amount should be very specific. Okay, you cannot take 50 ml of water and try to add some 50 gram of sugar or 20 gram of sugar. So that will not work, right? So the maximum amount of substance that can be dissolved in a specified amount of solvent at specified temperature is called as solubility. Okay, so understood? Any doubt from this definition of solubility for anyone? Can you all able to understand? If it is yes, just type yes in the chat box. Yes. Okay. Okay. Very good. Very good. So now the solubility, thank you so much students for your response. Now the solubility depends upon some factors. Okay. So it depends upon some 4 factors. So the first factor is it depends on the nature of the solute. Okay. The nature of the solute which we are taking. And it depends on the nature of the solvent also, and it depends on temperature, and at last it depends on pressure. So the solubility of any substance depends upon these 4 factors. Factors are very important. Just have a note of it. Okay. Solubility depends upon 4 factors: nature of solute, solvent, temperature, and pressure. Now moving forward with this, I am going to ask you one question. Okay. So all of you can able to see one picture on your screen, right? So what is this? What do you see from this picture? What is visible for all of you here? So we have some water. Yeah, very good, Rukmini. Yeah, good, Harish. So we have water and oil. Now tell me. Yeah. Now tell me why oil and water does not mix together. Oil and water doesn't mix together, so they are sitting separately, right? But can you give me the reason why? Why they do not mix together? Very good. Harish, you are doing great, you know. Like dissolves like. Very good. Yes. Yes. Very good, Rukmini. Your answer is also correct. Jain Mishimoga students are trying with the new term viscosity here. Okay. Okay, fine. So here in chemistry, so what do we say? Like dissolves like means the polar solute dissolves in polar solvent and non-polar solute dissolves in non-polar solvent. Okay, this is the meaning for this like dissolves like. Okay, suppose if I take sugar, sugar is a polar molecule. Okay, polar means plus and minus will be there. So water is a polar solvent because in water molecule, I have H plus and OH minus. So I have two poles, plus positive pole and negative pole. Okay. So that's why I call this water as a polar molecule. So the compounds which are having the positive charge and the negative charge are called as polar molecules. Okay. Now sugar, like water, sugar is also a polar compound, and to this sugar, if I add water, it will get dissolved because this is also polar and that is also polar. It will dissolve. Sugar will get dissolved in water. Okay. But if I try to add sugar in benzene, it will not get dissolved because benzene is non-polar. The formula for benzene is C6H6, right? So one is carbon and the other one is hydrogen. So in benzene, we cannot separate the charge into plus and minus, no? So it is a non-polar compound. So the polar sugar molecule will not get dissolved in the non-polar benzene molecule. Okay, so that is the meaning. And if I take oil, can you tell me whether oil is polar or non-polar? Can anyone tell me whether oil is polar or non-polar? Very good. Very good, students. Oil is a non-polar compound. So, this non-polar compound can only be dissolved in non-polar solvent, non-polar substance, right? But water is a polar component. So, that's why it is not getting dissolved. It is not getting mixed with the water. Okay, so this is the reason. And if I try to add oil in benzene, then there in the benzene solvent, oil will get mixed with benzene and it will get dissolved there. Okay. So the reason is like dissolves like. So you should know which compound is polar and which compound is non-polar. That is your duty to study. Okay. So here we have studied now for some compounds. Sugar, water, these are polar. Benzene, oil, these substances are non-polar in nature. Okay. So now with this concept, let's study the solubility of solid molecules in liquid. Now I am going to take a test tube which contains some solvent. Okay. And some solute particles are also inside this, and let me take this as a solution. Instead of solvent, let me take this as a solution. Now to this solution, if I add more solute, if more solute is added to this test tube, what will happen? Can anyone tell me? If more amount of solute is added to this solvent, what will happen? So the extra amount which I have added will get settled down at the bottom. All of you can able to see, right? So some solute particles here, they are settling down at the bottom. Okay, means they are forming a crystals. Yeah, it doesn't get dissolved, means they are nothing but crystals. So this is called as crystallization. This is called as crystallization. Okay. Now with this thing, I'll discuss some types of solution with you on the basis of saturation. Okay. I am going to take three pictures for you. So in the first picture, In the first picture, we have a solution already. Okay. And I'm going to call this solution as unsaturated solution. So what is meant by unsaturated solution? So more solute can be dissolved further. So all of you can able to see some four crystal particles coming down right to the solution. So if I can able to add more amount of solute to a particular solution, then that particular solution is called as unsaturated solution. Okay. So where more amount of solute can be added further. And the second thing is saturated solution. Second type of solution is called as saturated solution. What is meant by saturated? Any idea for anyone? Has anyone heard of this term saturated solution before? If you have heard of it, can you give me the definition for saturated solution? Unsaturated means I can add more amount of solute. Saturated means less amount of solute will dissolve. No, it is not like that. So no more solute can dissolve. Okay, no more solute. You cannot add solute to this. Even if you add, it will not get dissolved. In which no more solution can get added. Yeah, it is not solution, my dear Rukmini. It is no more solute. Yeah. Very good, Veena. Your answer is exactly correct. So no more solute can be dissolved in the saturated solution. Means that it has already attained a saturated point. You cannot add some more thing to get dissolved. Very good. The third type of solution is called a supersaturated solution. So here what happens? The solution becomes unstable and at last what happens? The crystal will form. Supersaturated means it becomes unstable and some amount of crystals will start forming inside the system, inside the container. Okay, it is called a supersaturated solution. So these are the three types of solutions on the basis of saturation. Okay, clear for all of you? Any doubt from this? Shall I go for the next slide? You want to note down anything from this particular slide or shall I move on to the next slide? Yes, how supersaturated? Sridev, how supersaturated means in what sense you are trying to ask? I'm not getting what you are trying to ask. Supersaturated means how supersaturated you are asking. What does it mean? Like I want to know how to make such solutions. You don't have to make, solution will be there. Okay. So we call some solution as unsaturated, saturated, and supersaturated. So in supersaturated, what happens? Already there will be some concentration for that solution. So we have studied many concentration terms, right? So there will be some concentration. If you add more concentration to that solution by adding more number of solute, what happens? Crystal forms. The concentration of the substance will be more and we call those solutions as supersaturated. Got it? Okay. So now let's discuss something which is very important from this topic. So which is the effect on solubility of solid in liquid solution. So two factors among four factors which I have already given you in the first slide, two factors will affect the solubility of solid in liquid solution. Okay. So the first factor is temperature. You might have already heard of this Le-Chatelier's principle in your class 11 equilibrium lesson. Okay. So what is Le-Chatelier's principle? When a system is subjected to any stress, it will try to nullify that effect by shifting themselves to the left hand side or right hand side to reach the equilibrium. That is Lee-Chatelain's principle. Now, I'm not going to discuss much about this Lee-Chatelain's principle. Now, according to this principle, so what is going to happen for the temperature? So, for the temperature case, for the temperature term, we are going to see two cases. One is case number 1. In that, if dissolution process is endothermic in nature. So, what is meant by endothermic? Can anyone give me the definition for endothermic? What is endothermic? Exothermic and endothermic. You guys have heard of those two terms, right? In your lower classes. The release. Will the energy get released in endothermic process? Rohit? Yes. Sridhar's definition is correct. So, if the energy is getting absorbed, then those processes called as endothermic in nature. And for those process, delta H, which is called as standard change in or the change in enthalpy value, that will be positive. For endothermic process, delta H value will be, positive. Very good, students. So in that case, if the process is endothermic, if means, I'll explain you a little bit clearly. Listen. So this is a test tube in which I have a solution. Okay. And I'm adding some solute particles inside this. And while adding the solute particles to the solvent particle, the test tube may become cold. Okay, so you can feel the temperature. The temperature will go down. Temperature will go down. So for this type of process, if I try to increase the temperature of that system, then the solubility will increase. If I try to increase the temperature of the system, okay, by heating it, the solubility of the solute particles inside the solvent molecule, inside the solvent particle will increase. In the case 2, if the dissolution process is exothermic, means on adding the solute, if the test tube is becoming hot, the heat energy is getting released from the system to the surrounding. Okay, in that case, the delta H value will be negative. And for those systems, if I try to increase the temperature, solubility will decrease. Okay, so this is very, very important. Please take a note of it. For endothermic process, increasing the temperature increases the solubility. And for exothermic process, increasing the temperature is decreasing the solubility. Okay, clear for all of you? So this is how the temperature is affecting the solid and liquid solution, solubility. Okay. Yes. Now moving to the next term, which is pressure. So can anyone tell me what is the effect of solubility of solid and liquid for pressure? How does the pressure is going to affect this solid and liquid solubility? Any idea? Very good. No effect. There is no effect. Does not have any significant effect. Yeah, very good. It is. The reason is because the solid and liquid are highly incompressible. So even if I try to give more pressure on the solution, there will be no effect on the pressure. So solubility will not affect at all. Okay. Pressure does not have any significant effect only in solid and liquid type of solution, not in all the cases. Okay. Only in solid and liquid type of solution, pressure does not have any significant effect. This is a very, very important point. Got it? We are ending up with the solid and liquid type of solution. I hope all the points discussed from this clear to all of you. If you have any doubts, you can let me know now. Otherwise, I will move on to the next topic. Shall I move on to the next slide, students? Yes or no? Yes. Now next we will go for gas in liquid solution and Henry's law. So if I discuss about Henry's law, you will understand gas in liquid solution because they are similar only. Okay. So straight away I'll go for Henry's law. So the Henry's law states that the solubility of gas in a liquid is proportional to, directly proportional to the partial pressure of the gas. The solubility of a gas is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Okay. So here you can see. Okay, I have some liquid molecules in the container. Okay. So this is the liquid molecule and some gas molecules. I'm putting some gas molecules inside this container. Now, on applying pressure, so I'm giving some pressure using piston. Okay, piston is the one which is used to give some pressure. If I try to give pressure to the gas and liquid solution, what will happen on increasing the pressure of the substance? What do you think? Solubility will increase. Solubility will increase. So that is what this statement says. Solubility of a gas and liquid is directly proportional to the partial pressure of the gas. Partial pressure means if I have two gases, then if I want to take out only the pressure of one gas, then I call that as partial pressure of the gas. Okay. So it is dependent on the pressure. Now I can write this in terms of P directly proportional to this X also. So what does this symbol X denotes? Can anyone tell me? What is the meaning of this X? Yes, very good. It is mole fraction, right? So X is nothing but the mole fraction. If solubility is dependent on pressure, then that pressure is nothing but the pressure of the gas, right? It is nothing but the pressure of the gas. So each gas molecules will have some mole fraction present inside it. So pressure is directly proportional to the mole fraction of the gas inside the container. So P is directly proportional to X. And if I remove this proportionality symbol, then I will introduce a constant which is called as KH. And that is called as Henry's law constant. And here P is the partial pressure of the gas in vapor phase. Okay, partial pressure of the gas in vapor phase. And X is the mole fraction of the gas in solution. Mole fraction of gas in solution. So this is Henry's law. P is equal to KH into X is called as Henry's law. And using this formula, we will solve many questions. Okay. So take a note of it. The definition and the formula is very important. P for pressure, KH is Henry's constant, and X is the mole fraction. Okay. Now, students, have you noted it? Shall I move on to the next slide? Okay. So now I'm going to take this formula and we are going to discuss few things using this formula. Okay. So I have told you that KH is a Henry's law constant. Means that KH depends on nature of the gas and the temperature. So how it depends on the nature of the gas and the temperature. So at a given pressure, if you see, if KH value is more, the solubility will be less. And if I try to increase the temperature, and KH value will automatically increase and the solubility will decrease. Okay, at a given pressure, if KH value is more, solubility is less. Means solubility is inversely proportional to the Henry's constant. Okay. So this relation is very important. You know why? So in some questions, they will give some four gases, okay, and they will give the KH value for all the four gases, and they will ask you to arrange those four gases in the increasing order of solubility or decreasing order of solubility. Okay, so in that case, you have to use this relation. The one which is having the highest KH value will be least soluble, and the one which is having the very least value of KH will be more soluble. Okay, so like this, you have to apply this concept, this relation, and you have to find out the answer for the question. And secondly, it talks about temperature. If temperature is more, KH will be more. In that case, solubility will be less. Okay. Some examples are also there. You know, right? So at low temperature inside the sea, if you see, at low temperature, the solubility of the gas will be more. Okay. In the very low temperature places, the solubility of the gas will be more in those cases. Got it? Now, I'm going to give you a graph which relates the partial pressure and the mole fraction. Okay. So the partial pressure is taken in y-axis, and I am going to take the mole fraction in x-axis. Since pressure and mole fraction, they are directly proportional to each other, we will get a straight line, because if one increases, the other one will also increase, right? So if pressure increases, the mole fraction will also increase. So I'm getting a linear graph with a straight line starting from the origin. Can you all able to understand this graph? Any doubt from this? Is everything clear up to this? Okay. So the last relation, solubility inversely proportional to KH relation, and this graph. So these two things are very important. Now let me discuss one application of this Henry's law. Okay. So I have taken the solubility of carbon dioxide gas inside this solvent. Okay. So all of you have heard of this carbonated drinks, right? This cold drinks. All of you are aware of this, no? All of you have had this, right? Yes. This cool drink. So what it is? Okay, let me take soda. Let me take soda. So what is soda actually? Soda is basically the dissolution of carbon dioxide gas in water. CO2 plus H2O. That is soda water, right? So carbon dioxide is a gas and water is a liquid. So it is gas in liquid solution. So how a gas is getting dissolved in that solvent? Water, by applying pressure. By applying pressure. So that's why the bottle is sealed. You know, right? The bottle is sealed. Means we are applying pressure so that the gas molecules, carbon dioxide gas, will get dissolved in the water. Okay. So this is one of the application of Henry's law. Now with this, we'll solve one question from this Henry's law concept. Here is the question for you. Very easy question, and you guys are going to solve. Okay. Henry's law constant for the molality of methane in benzene at 298 Kelvin is 4.27 into 10 to the power mm mercury. Calculate the solubility of methane in benzene at 298 Kelvin under 760 mm of mercury. How to approach this? How to approach this? So what is given and what is being asked? Any idea? So the pressure is given. Henry's law constant is given. Okay. Henry's law constant is given. And the pressure is also given. Now for this particular pressure, what is the solubility? We are asked to find out the solubility. So pressure is given as 760 mm of mercury. Do we need to find out the mole fraction? Yeah. And Henry's law constant, which is called as KH. So that is also given to us in the question. Now, according to Henry's law, P is equal to KH into X. And we are asked to find out the X, which is the mole fraction. By rearranging P by KH, we are getting the value of X. And this is nothing but the mole fraction. This is nothing but the mole fraction. Hence, the mole fraction of methane in benzene is 177.99 into 10 to the power minus 5. Okay. So, solubility here is nothing but the mole fraction. Got it? Very good, Rohit Munkalan. You have given me the correct answer. Students, is that clear to all of you? Fine. Fine. So let me summarize the things which we have discussed today. So we have studied light dissolves like concept, and then we have discussed about some effects which affects the solubility. Then I have discussed about the Henry's law, then some application of Henry's law. Okay. So this is all for Henry's law concept. Now the next topic is Raoult's law. Shall I move on to Raoult's law? Any doubt from Henry's law concept? Can you all able to understand each and every point which I have discussed? All the relations, definitions, graph, examples, application, everything is important. Okay. So this solution lesson is actually the physical chemistry lesson. So there will be some concepts, some formulas, some applications, etc., etc. Okay. So you just need to concentrate on those things, and you have to study. That is not the way. Then now coming to Raoult's law, the learning objectives under Raoult's law are, we are going to discuss about three things under this topic. First is the vapor pressure and Raoult's law. Then ideal solution and non-ideal solution. Thirdly, azeotropic mixture. So these three topics are going to get covered in Raoult's law. Okay. Now let's start from the first. Vapor pressure and Raoult's law. I have got a system for you. Okay. In which some solvent is present and some particles are present inside the solvent and some are present outside the solvent also. Okay. Actually, what is happening here? The particles which are present inside the solvent, they are coming out. They are coming out from the solvent. So what is the name of this process? If something is going from the container to the vapor as a vapor, what it is called as? If the particle goes out of the container, what is it called as? Very good. It is called as evaporation. Very good. It is called as vaporization or evaporation. Good. Now I am going to take one more system in which the particles which are present outside, they are coming inside the container. What does this called as? What is this? Very good. It is called as condensation. It is called as condensation. Very good. Now, if the rate of evaporation is equal to the rate of condensation, then I call the system as in vapor pressure. I call this as vapor pressure. If the rate of evaporation is equal to the rate of condensation, then it is called as the vapor pressure. The particles of that vapors, they will come and settle down at the surface of this liquid, and some pressure will be exerted by those particles which are settling at the surface of the liquid, and that pressure is called as vapor pressure. Got it? Clear for all of you? What is vapor pressure? It is the pressure in which the rate of evaporation is equal to the rate of condensation. Or you can say like this also, the pressure exerted by the liquid which is present on the surface of that liquid. Okay. Yeah. Now, we'll study about the vapor pressure of liquid-liquid solution. So here only the definition for Raoult's law comes. Okay. So what is Raoult's law? For a solution of volatile liquids, what does mean by volatile liquids? I may have two liquids. Both the things are volatile in nature. Volatile means the one which is getting evaporated. Both of the liquids are volatile liquids. For a solution of volatile liquids, the partial vapor pressure of each component, is directly proportional to its mole fraction. The partial vapor pressure of each component is directly proportional to its mole fraction. Again, P is directly proportional to X. But here in Raoult's law, this is same as that of Henry's law, right? So in Henry's law also we have studied the same thing only. In Raoult's law also we are studying the same thing. So what is the only difference? Henry's law is for gases and Raoult's law is for liquid. So this is the only difference between that law and Raoult's law. Okay. So to have that difference, I am going to change the proportionality constant. So there in Henry's law, I have used KH, right? So here I have taken P naught. If I remove this proportionality symbol, I will introduce a constant which is called as P naught. And this P naught is called as the vapor pressure of the pure component. Vapor pressure of the pure component. So this 0, which I am putting in the superscript, so that naught or the 0 denotes the pure component. Okay, P is the vapor pressure. P naught means vapor pressure of the pure component. So what is P then? P naught is vapor pressure of pure component. What is P? P is the vapor pressure of the solution. P is the vapor pressure of the entire solution. Okay, so you will understand this clearly in the next slide. Okay, so from this slide, you are taking the definition for Raoult's law and the expression for Raoult's law. I hope these two things are clear from this slide. Shall I move on to the next? Yes. So I am going to take a solute in one component, in one container. Okay, this is component number 1 in which liquid is there. The solute is a liquid here. And for this component 1, partial pressure of that component 1 is directly proportional to the mole fraction of that component. And removing the symbol, removing the proportionality symbol, I am introducing a constant which is P naught. And since this is for component 1, I am putting it as P1 naught. Okay, and here P1 is the partial vapor pressure of the solute. P1 naught is the vapor pressure of the pure component. Got it? Next, I am going to take the second component, component number 2. And this is a solvent. This is a solvent. And for this component 2, P2 is directly proportional to X2 and P2 is equal to P2 naught into X2, where P2 is the vapor pressure of the solvent and P2 naught is the vapor pressure of the pure component 2. Got it? Now what I am going to do, I am going to mix this component 1 which is a solute and the component 2 which is a solvent. So if I mix the solute and solvent together, I will get a solution. Yes or no? I will get a solution. Now according to Dalton's law of partial pressure, we have one more law called Dalton's law. According to the Dalton's law of partial pressure, the scientist Dalton said that the total pressure will be equal to the sum of the partial pressure. The total pressure of the solution is equal to the sum of the partial pressure. So if I take this, the pressure of the solute as P1, and if I take the pressure of the solvent as P2, then to find out the pressure of the solution, which is called as total pressure, what I have to do? P total is equal to P1 plus P2. P1 plus P2. And in the previous slide, we have studied that P1 is equal to P1 naught into X1 and P2 is equal to P2 naught into X2. So what we can do? In place of P1 and P2, we can substitute this expression. On substituting, I will get this relation. Okay. Now, while discussing the concentration terms in mole fraction concentration term, I have told you that sum of the mole fraction will be equal to 1. Do you guys remember that point? Do you guys remember this statement which I have given? X1 plus X2 will be equal to 1. Yes. Now, from this, what I am going to do, I am going to take X2. So, what is X2? X2 is equal to 1 minus X1. X2 is equal to 1 minus X1. So, in place of X2, I can substitute 1 minus X1 and the expression will become like this. Expression will become like this. Okay. Clear up to this? Students, any doubt till this? All of you can able to understand till this equation, right? Yes or no? Yeah. Okay. So now, what we can do? We can bring this P2 naught inside this. Multiply it with 1 and multiply it with the X1 also. I will get one step, right? What is that? P total is equal to P1 naught into X1 plus 1 into P2 naught is P2 naught and X1 into P2 naught is minus X1 into P2 naught. So this is the next step. And from this, which is common? X1 is common, no? X1 is common to both these terms. X1 is common to both of these terms. So what I can do, I can take X1 out. Before taking this X1 out, one P2 naught is standing separately, no? We can take that out first. So just take down P2 naught first, then take out X1 naught. If I take X1 naught out, then I will be having P1 naught and P2 naught. P1 naught minus P2 naught. So can you all able to understand the final step? Can you all able to understand that how we have arrived at this final step from this step? Just multiply this term, then take X1 separately out. You will be ended with P1 naught minus P2 naught into X1 plus P2 naught. Clear? Is it clear? Now, this equation, if you see, it is of the form y is equal to mx plus c. What is this y is equal to mx plus c? It is a straight line equation, right? So here y-axis is the total pressure and x-axis is the mole fraction. X-axis is taken as the mole fraction. And m is the slope. P1 naught minus P2 naught is the slope. And this P2 naught alone is the intercept. Now, taking x1 as x-axis, I mean the mole fraction as x-axis and the total pressure as y-axis, we can draw a graph. We can draw a graph. Okay. So in that graph, we can assume P2 naught is greater than P1 naught. So initially at this point, I have the mole fraction of 1 as 1 and the mole fraction of the second component as 0. Means at this particular point here, everywhere, I have only the mole fraction of component 1. Okay. Now this y-axis talks about the mole fraction. And in this point, in the second point, if you see, I have x1 as 0 and x2 as 1. Means entirely throughout this region, I have only the mole fraction of the second component and I don't have the mole fraction of the first component. Okay. So this y-axis is taken as the pressure and x-axis is taken as mole fraction. If I try to connect this P1 naught and this x, so this point is actually P1 naught. So here I have only the pure component 1 and here I have only the component 2. Okay. Pure component means here in this line I will have only P1 naught and in this line I have only P2 naught. In this point I have only the pure component 2. So I will have only P2 naught. If I try to connect this line, this will give me P2 and if I try to connect this and this This will give me P1. And if I try to connect this P1 naught and P2 naught, if I try to connect these two, that will give me the total pressure, which is nothing but P1 and P2. Clear? So if you try to look into this graph again and again, you will understand. So what I have taken, in the x-axis, I have taken the vapor pressure. In the y-axis, I have taken the mole fraction. So in this, I'm sorry, in the y-axis, I have taken vapor pressure. In the x-axis, I have taken mole fraction. Okay. So here in the first point, in point number 1, I have only the mole fraction of 1. Means only the component of 1 will be there. So only the component of 1 means pure component of 1. So P1 naught. And at this point, I have only the second component. So only pure component 2 is present. So it is P2 naught. If I connect those two, I will get the total pressure and each line is corresponding to P1 and P2. So any doubt from this for anyone? Is this graph clear to all of you? Vapor pressure versus mole fraction graph. Okay. So it's already 4, So let me stop the session here. We will continue this in the next class. Okay. So any doubt for anyone?
No, ma'am.
The solid and liquid solution and gas and liquid solution, which is called Henry's law, and something about Raoult's law. Okay. So in the next class, we will continue this Raoult's law. Okay. Thank you so much, students. Thank you so much for listening to today's lecture. Meet you all in the next session. Till then, take care. Bye-bye. Try to revise all the concepts which we have studied so far. Okay?
Okay, ma'am.
Thank you. Thank you so much for all of you.